Alrighty, so this video continues the discussion of the physics of rotational motion. We've done rotational kinematics, we've done torque, which is like the rotational force stuff. And now what we're going to do is try to consider conservation of energy, but now allow objects to rotate, to roll. So whereas before we may have had systems where there's a box at the top of a hill, the box slides down the hill, how fast does it go when it reaches the bottom? Now we may have a ball at the top of the hill and a ball will roll down the hill. Will that change anything? Because if you remember, what was important for conservation of energy was kinetic energy and potential energy. Kinetic, we knew, was 1/2 mv squared. And potential, depending, was, gravitational mgh, or 1/2 kx squared if it's a spring, and so on. And so what this said was, if an object's moving, it's got a velocity. And if it's got a velocity, then it has a kinetic energy. So anytime an object's in motion, it has some energy built within it that we call kinetic energy. But we didn't really think about it too much because obviously an object can move without having a velocity. For instance, you can have a spinning top or a spinning ball or a fan where the fan blades are spinning around. The fan itself doesn't have a velocity, it's not moving around the room, but the fan blades are rotating around. And so there's some motion associated with it, even though we can't say the fan has a velocity. So obviously, the kinetic energy we talked about before was not complete. That kinetic energy was only a linear kinetic energy. So that's the kinetic energy of objects moving linearly. Moves in the x direction, moves in the y direction. It has some linear velocity. There must also be some amount of energy associated with an object that has an angular velocity. And we saw, when we first introduced rotational stuff, that for every normal linear equation, there's a rotational or an angular equation where we basically just insert the rotational variables instead of the linear variables. So, kinetic energy, there's a rotational version, and that's going to be 1/2. The mass, the rotational version of a mass, is something called I, which is called the moment of inertia, which we're going to have to talk about. And of course, instead of v squared, we have omega squared. That's the angular velocity squared. Now for potential energy, that stuff's not going to change. That has nothing to do with motion. It has to do with location. So there's only the linear potential energy we're going to worry about. The only difference we're going to have for this version of conservation of energy is now that things can rotate, there's a second version of kinetic energy. So there's the linear, if a thing's moving left to right or up and down, and there's rotational, if an object is spinning. And so we're going to need both. Now, of course, in order to use this rotational version of kinetic energy, we need to know what was the conservation of energy equation. Well, let's just remember, it said the kinetic energy initial plus potential energy initial is kinetic energy final plus potential energy final. And we said before that potential energy stood for all the different potential energies that could be part of your system. So sometimes it's just mgh, sometimes it's just 1/2 kx squared, but we had some problems where the object went up a hill and hit a spring, so we needed both mgh and 1/2 kx squared. And we said, oh, all that means is wherever you see potential energy, you just have both potential energies. You add them up. Well, obviously, what we're going to do for kinetic energy is the same thing. When we say kinetic energy, what we really mean is the linear kinetic energy plus the rotational kinetic energy. And everywhere we see potential energy, we have gravitational potential energy plus spring potential energy. Now, sometimes you don't need both. Sometimes you only have gravitational. Well, that just means the spring one's zero. Same with kinetic energy. If a box is sliding down a hill, it's not rotating, so the rotational kinetic energy is zero. But if it's a ball, and a ball is rolling down the hill, then number one, the ball's moving, so it has a velocity, so there's linear. But it's also spinning, because it's rolling. And the spinning part has a rotational, so we'd have to add both. So thankfully, the key equation is still the same equation. All that we're doing is everywhere we saw kinetic energy before, there's now two. There's the original one we had before, 1/2 mv squared, and this new one to account for spinning. Well, that's good news. The next thing we need to worry about is, how do we use the rotational one? What is this moment of inertia? How do we account for it? Well, moment of inertia basically tells you about how easy it is to spin something or to rotate an object. Just as the mass tells you how easy is it to push something, so something with a lot of mass, if you want to push it up to a certain acceleration, it takes a lot of force. But if it's got a very small mass, then it only takes a little bit of force to push it to the same acceleration. That's what inertia is called. It's the kind of the object not wanting to move. It's resistance to movement. Well, the moment of inertia talks about the resistance of an object to trying to spin, to trying to rotate. And it's kind of the same thing. If it has a very high moment of inertia, then it takes a lot of torque, this rotational force, to try to rotate it. But if it has a small moment of inertia, then you only need a little bitty bit of force or torque to rotate it. So that's really what it means. How do we calculate the moment of inertia? Because obviously, you can have a whole bunch of different things that spin. You can have a wheel or a disc, a solid disc. You could have a hoop or a ring. You can have a ball, a sphere. Maybe the sphere is hollow. Maybe it's solid. Maybe you have a metal plate, a square plate. Or maybe you have a rod. All these different shapes can rotate. And if you remember something I said when we started talking about rotation and mass and things like that, I said where the mass is located makes a big difference to the torque. So if I have a rod like this straight rod here, if I hold the rod in the middle and I try to rotate it, well, it takes a certain amount of torque. I feel the heaviness in my wrist as I try to rotate this thing. But if instead I hold it from this end and I try to rotate the whole thing, that is a lot harder. It feels heavier in my wrist as I try to rotate this thing around. Even though the rod has the same weight, it's the same mass, it's just when I hold it from the end, most of the mass is out here, far away from my point of rotation. Whereas, if I hold it from the center, then the very end points aren't that far away anymore. So most of the mass is close to my point of rotation. So it's not as hard for me to rotate it. So what we have to imagine is different shapes will have different moments of inertia because where the mass is located is different. Let's say you have, for instance, a sphere, a ball. Well, you can have a solid ball, or you can have a hollow ball. Let's say this one's solid, and this one's hollow. It's hard to tell the difference from my drawing, obviously, but just imagine the hollow ball is like a basketball. It's basically an outer shell, but the inside is just filled with air. Whereas a solid ball is more like a bowling ball. It's solid throughout. There's no inner air pocket. It's all material. Don't worry about the fact that one's heavier than the other. Pretend they're both just as heavy as each other. So it's a really, really, really heavy basketball and a bowling ball that has the same mass. If you imagine a hollow one, if you look at the center of the hollow ball, all the mass is out at the edges. So all the heaviness, all the weight is far away from the center of this ball. It's out at the shell. Whereas for a solid ball, you have a lot of the mass really close to the center, and of course you got some at the edges too, but there's mass everywhere. So one would expect, since we already appreciate the fact that where the mass is located matters, that a solid ball will be different to try to rotate than a hollow ball will be. All right, if we can accept that this is true, then what we've learned is the shape of the object determines its moment of inertia. Now, there's a very formal mathematical way of calculating moments of inertia that has to do with calculus. And as you progress through more and more advanced topics, you learn how to do these calculations. If you're going to be an engineer, you're going to be a physicist, even a mathematician, you learn how to do this because it could be important. Maybe you're doing research. Maybe you're learning about bridge design. And you want to know, well, if I have a bridge, the floor of the bridge is like a rectangular plank. And maybe this, one of the pillars collapses. I want to know, how will this bridge fall? I want to be able to model it. I want to be able to predict what's going to happen. Well, the only way to do it is to be able to calculate for my particular bridge the way it's designed. It's not a perfect theoretical world. So I have to be able to mathematically calculate how the moment of inertia is, and that'll help me figure out what equations to use for the rotation, how much torque is going to be there, and all this kind of stuff. Well, we don't want to mess with it for our purposes in this class. What I'm going to do is I'm just going to tell you the little equation, the formula for the basic shapes we're going to worry about, and you'll just know what the formula is. You don't have to derive the formula. You don't have to use calculus and integrals to figure out what's the moment of inertia for a solid sphere rotating about its center, or what's the moment of inertia for a square plate about one of its corners. Each one of these types of things is a mathematical problem you have to solve. We're just going to get the answer and use the answer. So, first one we want to know is, what is the moment of inertia for a solid sphere? Well, the equation to calculate it, if you know its mass and how big it is 2/5 mr squared, where m, of course, is the mass of the sphere, and r is the radius. Okay, what about the moment of inertia for, let's call it a hollow sphere, or a ball? If it's a basketball, that's called a hollow sphere. It's a shell of a sphere, and the inside is empty. Well, for a hollow sphere, sometimes it's called a thin spherical shell, if you're going to be fancy engineer about it. That's 2/3 mr squared. Okay, what else? Well, maybe there's the moment of inertia for a solid cylinder. So this is something, cylinder looks like this. Let's say it's solid. And that thing's rolling down a hill or something. So the moment of inertia for a solid cylinder is 1/2 mr squared. If you notice, all moments of inertia come in the same form. It's always mr squared times a number. And the number is gotten from the shape. How is the mass located around this shape? When you do the mathematical analysis, you get these little coefficients, and each shape has a different coefficient. What if we have something like a hoop? Moment of inertia for a hoop. Or a ring is another way of saying it. You know, let's say we have a hula hoop, which would be like a ring of material and a hole in the center. And maybe that thing's rolling down the hill. So for a hoop or a ring, that's mr squared. So the coefficient for this one is just 1. And I think for the purposes of what we're going to be doing, these are the only ones we may come up with. Obviously, you can always Google table of moments of inertia. And there's all sorts of different shapes. You can have rods. You can have, well, what if I want to rotate it, but instead of it, like, for instance, this cylinder, I have the axis of rotation is the center of the cylinder. So it's rolling like you'd expect it to roll. You know, let's say you had a Coke can or something, and it's rolling down a hill. Well, it's where it's rotating about the center. But if this were some other thing, and instead of thinking about rolling, maybe you're rotating it. So you put it in a machine and you're going to rotate it, and this time you want to rotate it about this axis. So it's spinning like this way. Well, that would be a different equation, because now the mass is associated in a different way with respect to the axis. And so when you Google these tables, you're going to see, okay, you have a solid sphere, but what if the solid sphere is not rotating about the center, but it's rotating about some other point? Or you have a cylinder, but maybe it's rotating about the vertical axis instead of the horizontal axis. Don't worry about any of that. For the calculations we're going to have in this class, these are the only ones you need to know. And in fact, on a test, I will include the moments of inertia on the front page, so you don't have to memorize these. But just know that when you go to calculate conservation of energy and you have to plug in the moment of inertia of a certain sphere, what you're going to be doing is, instead of writing I, you're going to write 2/5 mr squared or something like that. So it's just an equation. That's all you have to worry about. All right. The only other thing you need to worry about is, remember, omega and V are related. If you have, let's say, a wheel, and the wheel is rotating with a certain omega, so maybe omega is, pi radians per second. That's how fast this wheel is spinning. Well, I could ask a question. I could say, if I look at this point on the wheel, and I watch it rotate around as this wheel is rotating, I'm following that point. I can ask, how fast does this point move as a linear speed? Or if this were like a big merry-go-round, and I'm standing right here on the merry-go-round, and this disc is spinning, I could calculate how fast I personally am spinning around the disc in terms of a linear velocity. And the relationship between the angular velocity and the linear velocity we've seen before. And what it is the linear velocity is given by the angular velocity times the radius. Where is the point of where is the point you're calculating? Okay. So that's another thing you want to remember. We have the moments of inertia, for the different shapes. We're going to plug this into our equation wherever we see an I. And probably when we see an omega, we're going to use this equation to change omega to V. And you're going to see why we do that. But just remember, there's always a relationship between the angular velocity and the linear velocity. If you know the angular velocity of an object, then you can ask, how fast linearly is a point on that object moving? And you would just use this equation. If I want to know this edge point on the wheel, then I'd need to know the radius of the wheel, r. If I want to know where this x is, how fast that part of the wheel is moving, then I'd use whatever this r1 distance is. It's not the radius of the whole wheel, it's only the distance from the center to the point I'm measuring. That's what r I'd use. But that's the equation. Very nice little equation. V is omega times r. All right, so all of that being said, let's put it all together and do a nice example. Here's an example. We have a hill. And we have, let's say, a solid sphere is at the top of the hill. If this hill is 10 meters high, then I'd like to find out how fast will this, will the sphere be rolling at the bottom? So two things to note from this question. Firstly, rolling. That means I have rotational energy to worry about. I'm not just sliding down the hill, I'm now allowed to roll. If I can roll, I'm spinning, so I need rotation. Second thing, if I ask how fast am I going, what I'm asking is linear velocity. If I want the angular velocity, I'd ask for the angular velocity. If I just say how fast, take it to mean what's the linear velocity v. Okay. Now, firstly, it seems like there's not very much information given in this question. All I know is I have some hill, the shape of which I don't know anything about. All I know is I start 10 meters up in the air, and eventually I get down to the ground. Maybe there's bumps, maybe there's wiggles, I don't know any of that. Number two, I only know the shape of the object. It's a solid sphere. I don't know how heavy it is, how much mass, how big, I don't know any of it. So this is worrisome. But let's proceed and see how far we can get. If I need more information, then I'll have to ask for it or something like that. So let's go. What's the equation? Well, the equation is conservation of energy. Kinetic initial plus potential initial is kinetic final plus potential final. Because I'm rolling, that tells me there's two kinetic energies here. There's a linear and a rotational. So I put them in. Kinetic energy linear, 1/2 mv squared. Initial. Kinetic energy rotational, 1/2 I omega initial squared. So those are my kinetic energies. Potential energy. Well, what types of potential energies are in this problem? Well, there's gravitational, because I'm going from 10 meters high down to the ground, so there's a change in height. Is there a spring? There's no spring in this problem, so I don't worry about it. All I have is mgh. All right, so that's the initial stuff. I've got two pieces of kinetic, and I've got a potential. And now I'll look at the final side. I've gone down to the bottom. Kinetic, again, I'm rolling, so there's two pieces. 1/2 mv final squared plus 1/2 I omega squared final. Okay, that's kinetic. And potential, again, there's no spring at the end, so there's only mgh. All right. Now, let's ask the questions, just like we did before. Initial state, I'm at the top of the hill. I have not started rolling yet. At that point, am I moving? No, I'm not moving. So, no velocity initial. So 1/2 mv squared is 0. Second question, this is an extra one now. Not only am I moving, am I rotating? Am I spinning yet? Well, no. Again, I'm just sitting there at the top of the hill. If I haven't started moving, certainly I haven't started spinning either. I'm not rolling yet, so 1/2 I omega squared is also 0. Both pieces of kinetic are 0 at the beginning. Third question. Am I at some distance above the ground? Sure, I'm 10 meters above the ground. So there's an m times a g times a 10. Initial state is done. Now we look at the final state. Final state. I've rolled down the hill. I'm at the bottom, rolling along. At this point, am I moving? Sure, I'm still moving. Nothing has stopped me. There's some 1/2 mv squared. Okay, am I rotating? Well, if I'm moving and I'm a ball, and I've told in this problem that I'm rolling specifically, I'm not sliding, then if I'm moving, I must be rotating as well. So yes, there is rotation here. So 1/2 I omega squared. Last question. I'm now at the bottom of the hill. Am I some distance above the ground? No. I got all the way down to the ground level. I'm at 0 height, so mgh is 0. All right, so now, what do I want to solve for? I'm looking for v. How fast? Okay. Can I solve for v? Well, here's v. What are my unknowns? Well, g, that's 9.8. That's okay. M, do I know M? M is not given in this problem. But, if you remember, sometimes M cancels out. Does M cancel out here? There's an M on this. There's an M on this term. Uh-oh, there's no M on this third term. M doesn't cancel out. So it looks like there's an extra unknown sitting there. In fact, there's also I. I don't know what I is. And I don't know what omega is. There's a whole bunch of unknowns in this problem. But there's only one equation. Certainly, I don't have 4 equations to use. But do I? Remember, I gave it away earlier. I said anytime you see an I, you're going to be replacing it with one of these things. Well, which I do I have for this problem? I have a solid sphere. So, I look back at my table. I for a solid sphere is 2/5 mr squared. So what I'm going to do is everywhere I see an I, I'm just going to replace it. So let me leave this alone. Let me leave this alone. And now I have an I. Instead of writing I write 2/5 mr squared. All right, what about the omega? I could do the same for omega. On this screen, I said, here's a relationship which tells you how to go between v and omega. Omega is v over r from that equation. So that means everywhere I see an omega in my equation, I could just replace it with v over r. So let's try it. Let's see what happens. And maybe this won't work. I'm not going to promise it works. But this is what you do when you're trying a problem that you've never tried before and you seem to be stuck, you try things out. You test what you can do, and sometimes you find your way through it. Here I have an omega. Instead of writing omega, I'm going to write V over R. But remember, it's omega squared, so it's V over R squared. All right, does this help? Am I any closer? Well, remember what the problem was. The problem was there were too many unknowns. I couldn't cancel anything. Can I cancel anything now? Well, let's check the m's again. There's an m on the first term. There's an m on the second term. And now there's an m on the third term. Aha! M's cancel. That's really good. We got rid of an unknown. What else is unknown? G is 9.8. That's not a big deal. V, that's the thing we're looking for, so leave that alone. What about this R? I've got an R squared sitting here. But if you look, there's an R over here, and that R is also squared. So let me clean this up a little bit. Instead of writing V over R quantity squared, well, V over R squared is the same as V squared over R squared, right? V over R, the whole thing squared, is the same as V times V over R times R, which is V squared over R squared. So notice, this R squared cancels this R squared, because one's on top, one's on bottom. So now, what are our unknowns? I've got a V, I've got a V here, and that's the only unknowns. That's perfect. I can solve this problem. So let's try to look at it. G, 9.8, times 10 equals 1/2 V squared plus. All right, let's multiply this stuff out. I've got a 1/2 times a 2/5. So this 2 cancels this 2, and I'm left with 1 over 5. This m had canceled, this r had canceled, so I just have a v squared. Well, that's a lot prettier. So 9.8 times 10, that's 98, equals, here's a little fraction math. You have to remember, how do you add fractions together? 1/2 plus 1/5. You have to get common denominators. What's the common denominator? 10. So 1/2 becomes 5 over 10, and 1/5 becomes 2 over 10. So 5 over 10 plus 2 over 10 is 7 over 10. So 1/2 v squared plus 1/5 v squared is 7 over 10 v squared. All right, so solve this for v. I get v equals square root of 10 times 98 over 7, which, if you get out your calculator, 98 times 10 over 7 square rooted 11.83 meters per second. And there we go. Here's a conservation of energy problem, where now the object's not just sliding down the hill, which is what we did a few weeks ago. Instead, it's rolling. What does that do? It adds one term. Instead of having just kinetic energy, 1/2 mv squared, there's two kinetic energies. One for the linear motion, one for the rotational motion. But everything else about the equation is the same. You might have springs, you might have gravity for potential energies, and so on. You ask yourself the same questions when you're trying to figure out what terms to keep. In the initial state, am I moving yet? Am I rolling yet? Am I some distance above the ground? Am I compressing a spring? That tells you what terms for the initial state, and of course you ask the same for the final state. The difference now is once you've done all of that, the next thing you have to do is replace I, the moment of inertia, for whatever shape you have in your problem. And then replace the omega with v over r. Once you've done that, a whole bunch of stuff cancels out, and you're only going to have V as your unknown. The numbers might be different. Instead of 2/5, it might be 2/3, it might be 1/2. It depends what's the thing rolling. But once you get to this point, you should be able to handle the little bit of algebra to find your V. And that's all there is to it. It's very, very little extra for this than there was for the original conservation of energy. We do add an extra term, but eventually the I goes away for whatever I means, and the omega goes away for whatever omega means in terms of V. And then you're left with the same type of equation you had before. Solve for your V or whatever thing you're solving for. Maybe you're solving for the height or whatever. It's going to be exactly the identical questions from conservation of energy before, only now instead of the thing sliding, it's going to be rolling. Now, it takes a little practice, this part right here. I'll put it in red. How to replace the I correctly and the omega correctly, and then cancel what you can cancel. Do 1 or 2 practice problems, and you'll be used to it, because you're going to do the same cancellations every time. But you have to do it a few times first yourself to make sure you understand it. Once you understand it, then if you knew how to do conservation of energy before, you still know how to do it now, which is really good news. Now, the only other thing I want to state before I end this video is if I ask for the angular velocity, you have 2 options. So first of all, here, ask for the speed. How fast? That's the linear velocity. That's get rid of omegas and give me V's. If instead I want to know what is the omega, I don't know the V, I don't want the V, I want the omega, well, you could either solve for V, just like we did with this example. So do exactly the same thing and get your V. Then use V is omega times R, or omega is V over R to calculate omega. Once you know V, divide it by the size, the radius of the ball or whatever it is, and you have your omega. So in order to do that, I'd have to tell you what R is in this problem. I would have said the sphere has a radius of 0.3 meters or something. Or the other thing you could do is the opposite of what we did. Change all V's to omegas. So everywhere you see a V, you would use omega times R. So for instance, this V right here, you'd call it omega times R, quantity squared. And then you'd have an equation with just omegas in it, and no V's anymore. Again, I'd still have to tell you what the R is, because now there's an R sitting in your problem. But I would tell you in the problem. And so you'd solve, instead of solving for V like you did here, you'd solve for the omega that's in the problem. So which thing you replace? Do you replace the V for omega, like we did here? Like we do here. Or do you replace the omegas with V's, like we did in this example? They're both the same thing. It just depends on what the question's asking. If you don't want to worry about, well, if I want omega, I have to do this other thing, then just do this way, which is this first option. Solve it like we did this example. Solve for your V, get V, even though you don't care what V is. And then once you have your V, calculate omega from it. Divide it by R, that gives you omega. So That's perfectly fine. If you say, look, I only want to remember one way of doing things, I want to remember how to do it this way and only this way, then do it. And if I ask you for omega instead, you go through the process, you get your V. I now know V is 11.83. And all I'd say is, okay, that means omega is V over R, so it's 11.83 over 0.3 meters, and you get whatever omega is. You know, it's just one extra little step at the end. If you don't want to have to go through the extra step, then you do the second option, which is up here, where you calculated, instead of having the omega and you put V's instead, well, you do the opposite. Everywhere you saw a V, you'd put an omega. Anyway, I hope that's clear. So, this is it. This is conservation of energy with rotational motion. The only thing that could change is, well, what's the shape of the object? Is it a cylinder? Is it a ring? What's rolling down the hill? And if you just have this little table of values here, of course, like I said, on any exam you have, it'll be there on the exam for you. You don't have to memorize these. But you just have them when you're working these problems. Then everywhere you see an I, you replace it with the appropriate I. And then go back, look at all the old conservation of energy problems we did before, all those practice problems and homework, and just replace the object on the hill with one of these shapes. So, you know, you had, here's a hill that goes to B here, A's down here. Well, let's say you have a cylinder. Okay, and the cylinder rolls down a hill and goes up to B, where B is at 5, and the original height was 20, or whatever. I know you recognize this problem from the past. Well, before it was a box slides down the hill. Well, now make it a cylinder rolling down the hill. How fast is it rolling at part B? Or it's a ring. A ring is rolling down a hill. How fast is it at A? How fast is it at B? It's the same problems. All you're doing is adding this extra rotational conservation of energy equation. This one right here. All right, so that's it. Until next time.